Hi folks, we're going to take a look at number 3 now from the Unit 7 quiz. Here we've got Horace and Doris are training for a marathon. Horace lives 20 kilometers directly north of Doris. Okay, so let's say this is Doris's house. Okay, and Horace lives up here 20 kilometers to the north. Okay, so this distance is 20 kilometers. Okay, at 9 a.m., they both begin their runs from their respective homes. Horace jogs southward at a speed of 8, and Doris eastward, okay, so south and east, at a speed of 6 kilometers an hour. They both run for 2.5 hours. So we want to know when are they closest together and what is their minimal distance from each other. Okay, so let's try to represent here what's going on. So first of all, we see he's coming south. She's going directly east. So we know that their motion is at a right angle to each other. So that's always nice, usually helpful. Okay, so let's represent the run that Horace is doing. So he's going down. Okay, so that's his motion. And we'll make Doris's a little smaller because she's not running quite as fast. Okay, so this represents their run for a particular time. So just to indicate that that is right angled. And what we're interested in is the distance between them. Okay, so I'll use capital D here because I suspect I'm going to have to use some derivatives at some point. I don't want it to interfere with my notation. Okay, so we're trying to find this minimal distance, and we see that one relationship that we have is this right angle triangle, which includes the distance between them, that's the hypotenuse, includes the distance that Doris will have run. Okay, I guess we'll make this DO to distinguish it from the distance. Okay, but notice that this side of the triangle is not the distance that Horace has run, but the remaining distance to Doris's house. Okay, so let's keep that in mind. Okay, so since we're dealing with distances, okay, but what we're given is speed, okay, and what we're looking for is the time at which they're closest together. So if I can use the time to help me write out some equations, that would be useful, and that is useful because here, if I want to represent the distance that Doris has run, say at time t, well, that's just her speed times the time that she's been running. Okay, so this would be she's running at 6 kilometers an hour times t, whatever time she's been running. Okay. Similarly, if I represent how far Horace has run, well, his would be 8 times t, 8 kilometers an hour times that same time unit. Okay, but I need to create a relationship with that side there. So if the total distance is 20, this is going to be 20 minus 8t. Okay, this is why the diagram is so important because it really helps you to distinguish what it is that you're actually using, what is going to be useful to you. Okay, so now I can create a relationship between the distance between them and these other two distances that are given with respect to time. Okay, so I'm actually going to avoid using square root here because I think I can just use implicit differentiation. So I'll write it out as d squared equal to 6t squared, okay, which is this side of the triangle plus that side of the triangle squared. So 20 minus 8t squared. Okay, and now what we want to do is take the derivative of both sides of the equation. Okay, so I can, I suppose, multiply all this out, or I can again just use the chain rule. So I think I can avoid actually multiplying all this out. If you did do it, perfectly fine. But let me take the derivative of both sides with respect to t. So here, this is capital D squared with respect to t. So first I take derivative of d squared with respect to d, which is 2d, times the derivative of d with respect to t. Okay? Now here, let's take a look. We have a derivative of 6t squared. So this is 2 times 6t to the exponent 1 times the derivative of 6t, which is 6. So you see how I use the chain rule instead of multiplying it out. In this case here, I don't think I saved too much time, but I might in this one here. So if I take the derivative of the second expression now, this is going to be 2 times 20 minus 8t to the exponent 1 times the derivative of 20 minus 8t, which is just negative 8. Okay? So, since I'm trying to minimize the distance, I want to determine when the derivative of the distance is equal to 0. Okay? So if I make this expression equal to 0, you see that this 2d doesn't even come into play. Okay? Because it just multiplies here. So I've got 0 is equal to, and now I'll start simplifying, but you see now I'm not squaring any binomials. Okay, so here we've got 6 times 6 is 36 times 2 is 72t. Okay, and so here we've got 2 times 20 is 40 times negative 8, so this is going to be minus, well, 4 times 8 is 32, so minus 320. Okay, and then here we've got 2 times negative 8t, so negative 16 times negative 8. Okay, or if we go the other run, might be a little easier. 8 times 8 is 64 times 2. So that's going to give us plus, let's see, where am I at? So that's going to give me plus 64 times 2, 128. Okay. So now let's simplify a little more. So here we've got 128 plus 72. Well, that's exactly 200t minus 320. And now we can solve this equation. 200t equals 320. So t is equal to 320 over 200. Let's figure out what that is. Okay, so 320, whoops, 320 divided by 200 is 1.6. Okay. Okay, now let's test out the to see what our minimum distance is going to be. Now, one thing I didn't do earlier on is take a look at what our constraints are on the variable. So now that I remember that I really should be doing that, because yes, this is the critical point, but I believe that this is going to be a closed interval that we're working with. Okay, so time, you can't go before they started. So at the start, in fact, you know what their distance is at the start. He's leaving from home, she's leaving from home, so their distance is 20 kilometers, but that's going to correspond to t equals 0. So t has to be greater than or equal to 0, and they give us an upper bound. They say they run for 2.5 hours, okay? So we're not interested with any time past 2.5 hours, so it has to be less than or equal to 2.5 hours, okay? So this critical point that we found does lie within our domain, but because it's a closed interval, we have to check the critical points and the two endpoints, okay? So let's do that, okay? So if we determine the distance when t is equal to 0, well, as I said, we don't actually have to stick that into the equation. We know that at the beginning, they're 20 kilometers apart, so I can just put that in, okay? Let's calculate their distance at the end at 2.5 hours, okay? So now we have to go to our distance formula here. So we're going to be taking d is going to be the square root of this thing here. So the square root of 6 times 2.5 squared, okay, plus 20 minus 8 times 2.5 squared, close off our bracket, and so here we have 15 kilometers. So at the end, they are closer together. Not too surprising since Horace does seem to be running a little faster, but let's see if the distance at our critical point of 1.6 is even smaller. So again, notice that I'm not checking whether this is a max or min or neither, because in the end I have to check the critical points and all the endpoints. So I might as well make my determination after I've done that. So let's do the square root of 6 times 1.6 squared plus 20 minus 8 times 1.6 squared. And here we have 12. So in fact, this is a shorter distance. Okay, so according to this, at time 1.6 hours, they'll be at their shortest distance of 12 kilometers. And in fact, those are exactly the questions that they're asking me. Okay, so they are closest at 1.6 hours from start. Okay, that is, well, let's see, they started at 9 a.m. So we add 1.6 hours. So let's calculate what 0.6 hours is. So 60% of 60, well, should be able to figure it out. It should be 36. And there you go. So 1 hour and 36 minutes. So that is at 10:36 a.m. And their minimum distance from each other is equal to, well, we found out here that it's 12 kilometers. Okay, so again, what we do is we use a diagram to come up with a model, okay, that we can use to optimize. In this case, here we want it to minimize. We find our constraint on the variable, do the calculus, and then make sure we're actually answering the question that is posed. Okay, that's it for this one.